Um, okay.
I'm sure you can figure it out, right?
Alrighty. Now, we're still in the section on separable equations, focusing on what are called homogeneous equations, and I'll return to that in a moment. But a very quick recap, besides this is relevant for the homework going on now. Yeah, this is going to be fun. Okay. So far we've only covered two types of ODEs in terms of actually learning how to solve them. There's a linear case and I'm going with this pretty generic form of writing them, and it's a good idea to try to get them in this form so that all the solution formulas I gave will apply, where you have, yeah, definitely off my game today. I'll have to be more careful. So linear equation where you have y only appearing, no function of y, just plain y by itself in the equation. And you have coefficients p of t and q of t that could be whatever functions of t. So when we say linear, we really mean linear in terms of y, not t. And for this case, we have an explicit solution formula. In terms of the integrating factor, u of t. And don't forget your plus c, which would be used to satisfy whatever initial condition you're given. That's the subject of the exercises from a textbook for all of this form. And then there's separable equations. Y prime is equal to some function of only t times some function of only y. And so what we have is, in this case, we do not necessarily have an explicit formula for solution. It depends on the equation. But what we do have is an implicit form, where we have integral of minus g of t dt plus the integral of 1 over h of y dy is equal to 0. And that really just comes from rearranging this equation. 1 over h of y dy is equal to g of t dt, where what I've actually done is, because since y prime is the same as dy dt, what's done here is you're breaking, if you treat dy dt as an actual fraction. So dy stays on this side, and then dt moves to the other side. Now, that's not really all that rigorous. It's just a good way to think about how to do these problems. Really, what happens is then we integrate both sides with respective variables, y on the left, t on the right. And the reason why this is justified, I showed earlier, because really what you're doing is you're actually integrating both sides with respect to t. It's just that on the left side, you're able to do a u substitution to get rid of t altogether and think only in terms of y. So, all right. Now, so I want to point out, I try to give explicit solution formulas whenever possible. It's not always possible. And other times there's more of a procedure to follow. And with this here, we only have two entities that make equation specific, p of t and q of t. Once you have p of t and q of t, then bam, with your formula, there's not really much to know there. You just get your integrating factor, and then you can work out your solution, work out the integral. Here, the idea is because we call it separable, we separate. Put y on the left side, t on the right side, integrate both sides. And that leads to this. And what happens is, after you do this, maybe you can solve for y. It just depends on the problem. But if not, that's okay. All right. Now, under this kind is what I started at the end of last time, a homogeneous equation that, strictly speaking, is not separable. But it can be written in terms of, for right side, it can be written as a function of just y over x. And for example, if all the terms have the same degree, there's really only a limited subset of equations that you can use this for. So this is how you classify an equation as homogeneous before you actually try to solve it. And as a result, you make a change of variable. V equal to y over x. And that leads to this modified equation. This is what I did at the end of last time. X v prime plus v is equal to this function f, but now y is eliminated and written in terms of v. So now v prime is equal to f of v minus v over x, and this is separable, where your g is 1 over x, and your h is f of v minus v. Okay. All right. So that's where too many parentheses. So that's where I ended last time. So now what I'll do is I'm going to step through an example of a homogeneous equation so you can see how you can apply these ideas to solve it. Okay. So as an example, and this is written in a rather strange form. Well, actually, I'm not going to do that. Okay, so we have x squared plus 3xy plus y squared all over x squared. Now, if you look at all the terms in the numerator and denominator, all terms have the same degree 2 in this case. And one thing you can do is simplify this equation. So we have, so if I were to break this up into 3 fractions, a sum of 3 fractions, what would that be?
1 plus 3y over, 3y over x plus y squared over x.
Yeah. Okay, so after breaking up the 3 terms and then simplifying them as much as you can, this is what you get. Now I'm going to go one step further with this last term, y squared over x squared. Of course, you can write that as y over x quantity squared. I should mention, one of the other classes I teach is Math 102 online. And I got an email from a student trying to work out a problem where they had a situation dealing with a fraction like this, except it was inverted. There was a sum of terms in the denominator, and they thought they could break up a fraction that way, as opposed to this case where the terms are in the numerator. And so that's one of those no-nos, and it's not all that surprising to see something like that at this level too, which is why I'm warning you about it now. Don't do that. If you only break it up, if you have this situation, you have a sum of terms in the numerator, not the denominator. Okay, so now with v equal to y over x, you have 1 plus, I can express this in terms of v now, 3v plus v squared. So this is your f of v. So that's what's happening on the right side of your equation. So your new ODE, after you change the left side, is you get x. You get v plus x v prime. So this is what y prime becomes, and this is how these homogeneous equations always work. So this, regardless of the particular problem, this always happens. And I should mention, in case you don't have this memorized, if you get to a point where you know it's a homogeneous equation, you know you need to do something to the left side, and you don't remember that it's this, that's okay, you're not sunk. This comes about by applying a product rule on this equation, where you rewrite it. Because if v is equal to y over x, that's the same as saying y is equal to v times x. So if you remember at least this, and for this kind of situation you should remember at least the change of variable that's being made, that would give you this, and you have the left side that way. So now my new ODE is v plus x v prime is equal to f of v, which in this case is 1 plus 3v plus v squared. Okay. So now, any questions up to this point? So now what we want to do is, this equation is separable, so we want to solve it that way. So I'm going to simplify. So x dv dx is equal to 1 plus 3v plus v squared. And then this v, moving it to the other side, 1 plus 2v plus v squared. Okay. So now in the usual form, for separable equations, we have 1 plus 2v plus v squared all over x. So we have g of x times h of v. So I'm writing this the same way as I write separable equations generally. So this is equal to 1 over x, and this is equal to 1 plus 2v plus v squared. So now what you can do is solve this equation just like any other separable equation. So, what we want to do is separate. Get everything x on one side, everything v on the other side. So what you have is 1 over 1 plus 2v plus v squared d v prime is equal to 1 over x dx. So now the left side depends only on v, the right side only on, whoops, sorry, should not have done that yet. So you can think of this as dv dx is 1 over x. And now, again, I don't like doing this because it's not really rigorous, but if it's a way that works for you, then by all means do it. I can move this dx to the other side. And then you can integrate both sides with respect to their respective variables. So this is how you, at this point, it's not even dealing with a homogeneous equation. This is just how you deal with a separable equation. Okay. On the other hand, if you prefer the solution formula, that I gave last time, you can just go with that, and that would get you to this exact same point. So depends on how much you feel comfortable committing to memory. Because on a test, you can either have a solution formula off the top of your head and just blast that solution out quickly, or if you don't think you can remember that, you can just keep in mind, okay, it's separable, so you go ahead and separate and integrate both sides. It's up to you. Okay, now, so for integrating this, what should we do with this integrand, 1 over 1 plus 2v plus v squared, before proceeding? Well, yeah, for a rational function like this, normally that's what you would do. How does this factor? Yeah, this is a perfect square. So yes, these problems can try to work out that way. 1 plus v is quantity squared. Okay, so we're just focusing on the left side integral because the right side obviously is not going to be a problem. Now, it turns out though, normally if this is factored into like v plus 1 times v plus 2 different linear factors, then yes, you would need to continue with partial fractions. We actually don't need to do partial fractions in this because this is decomposition. This can be integrated right away. Now, I should mention, of course, you're all familiar with the power rule. Integral of x to the n is x to the n plus 1 over n plus 1 plus c. But you can get a little more general with it. Suppose you have some constant in here, x minus c, all raised to the n power. Then this applies. Okay, that's as general as you can get. So now, the way you can justify this is through a u substitution. U is equal to x minus c. So if you want, you can go through the mechanics of doing a substitution and so on, and have like du is equal to dx, etc. Or you can just know this and save yourself some time. So, catching a pattern help, I'm giving you lots of tips to help you save time. And even though I don't take tests anymore, they save me time too, and that's important. Okay, so this can be rewritten as 1 plus v to the minus 2 dv. So now you can go ahead and integrate, and what would you get? Yeah, because 1 plus v to the minus 1 over minus 1. So that's power rule right there. And I'm actually not going to throw in a plus c just yet because I'm going to use it on the other side. Okay. All right. So that's the left side. And then on the right side, of course, we have natural log that's the value of x. And there I'll put the plus c. When you have indefinite integrals on both sides of the equation, you do the integration, you only need 1 plus c because it's arbitrary. So now, both sides have been integrated, the v side and the x side. So v satisfies this equation. I'm just going to put everything on one side to get rid of clutter. So we have 1 over 1 plus v plus natural log of x plus c is equal to 0.
Is that not supposed to be made?
That's why I'm saying I'm putting everything on one side. Yeah. So, all right. So now v satisfies this equation. So what we can do now is see if we can solve for v. And it turns out in this case, we can. And do I have? All right. For this problem, I don't have initial condition. So we're not going to solve for c explicitly. Now, so how do we go about solving for v? What should we do algebraically? just one step. You have to jump for and
So you would subtract one minus ln of absolute value c minus absolute minus c, and then multiply by b.
I'm sorry.
You would subtract the ln of x.
Yeah, move it to the other side.
Yes.
Yeah, let's just do one step at a time so everybody can follow along. Okay.
And then you would subtract 1 from both sides, and then multiply by b.
No, what we need to do at this point is, because we have v in the denominator, we need to flip.
Yes.
Okay, so flip both sides, we get v plus 1. And now, whoop. Sorry, that's messy. And as I recall myself saying, you flip both sides. Yeah, and now you go ahead and move the 1 to the other side. So you get v is equal to minus 1 minus, and what I've done, I'm just pulling a minus out of this. So now in the denominator, we have a plus. Okay, so that is v, but we came here for y. What should we do to this solution to actually get y? The answer is somewhere on the board. Yeah, y is equal to vx. So I'll box this. Whoops. Okay. I'll box the final answer. Y, which is equal to vx, is equal to minus v minus, x. Minus x over natural log of x plus c. Okay. Any questions on the process? Admittedly, it's kind of a pain. But the bulk of the work was on the separable equation we got. So the idea is, see if it's homogeneous. If it is, use a change of variable, v is y over x, get a separable equation from it, and that will always work that way. And then go ahead and solve a separable equation like any other separable equation. The next homework 2, is going to be all about separable and homogeneous equations. All right. We have nearly half the class time left. So let's have some homework questions.
We go over 28.
28. I knew someone was going to ask about 28. 28 is definitely, well, all right, it's my favorite problem, but which means it might be both of you, hopefully also least favorite. Because of course it's important to give questions, problems that are more basic, like here's an ODE and solve it. That's one of really the essential things for this whole class is that you're equipped to solve various kinds of differential equations. But in a real application, the process doesn't stop there. You obtain a solution, and then you want to know something about its behavior. And I expected that y'all would get stuck with this, even if solving the equation itself might be a problem. There's what else they ask. Okay. So this is 2.1, number 28. So we have y prime plus 2/3 y is equal to 1 minus 1/2 t. And then just a generic initial condition. Y is 0 is equal to y naught. So you're supposed to solve the equation like any other linear equation. Now, does anyone encounter any problems with that part of it, just solving the equation? Okay. Because that part is like there were problems. but I'm going to get the wording correct here. Okay, so find why not so that your solution touches does not cross the x-axis. Okay, so imagine you're applying for this homework set, saying solve this equation, even solve this equation, and then you got to that, and your brain went right. Okay. So my goal here is I do want to help you guys get moving on this problem without giving too much away. So I'm going to list you guys to work out a couple of details that I'm hoping will then get everybody moving on this problem. Because the problem is everything is described in words. And you need to know in terms of equations, what does that really mean? And for that, you actually fall back on ideas from Calculus 1. What I'd like someone to do is, well, actually, before I continue, so what I'd like someone to do is, can they show me, by drawing, either on paper, or you can come to the board if you want, I don't care, an example of the graph of a function that exhibits its behavior. We want to make sure we're all on the same page. So what does it mean visually for a function to touch but not cross the x-axis? Okay, and we have a volunteer right here. And can I show everybody?
Yeah.
Okay, I don't know how well you can see, but okay. Actually, I'm going to reproduce it and make it bigger.
Great.
All right, so what he drew was this. I'll draw it carefully. And in fact, I'm going to make it a little more general. Because it looks like the way where you had it touching and crossing was right at x equals 0. Or actually, we're at the t here. So this kind of behavior, if it's the same thing but shifted, is also acceptable. So it is. So we do have it just basically resting on the x-axis, as opposed to crossing the. Okay. Oh, the problem's in the t-axis. Sorry, but your horizontal axis, which is normally think of it as the x-axis, but this problem is t. So here's crossing the t-axis. As opposed to just touching. So this is not what we want. Okay, so if this is our solution, y of t, and the problem says, okay, well, we're asking find a value of y naught for which this happens somewhere. If we're not specifying where it happens, that's something for you to solve for. So I'm going to name this point. I'll call it T star. So T star is this magical point at which the solution touches but doesn't cross the axis. So the question now becomes, what is true of y of t at this point? What we want is an equation. We want to move past words here, because once you have equations, that's something you literally work with. So, what kind of mathematical statement can we make about how y is behaving at that particular point?
Derivative is 0.
Yeah, the derivative is 0. So y prime of t star is 0. Now, what else though? There's one more thing that also applies at this point. In fact, it would apply to this case or this case. What?
They're plotted for their positive?
No.
Y is equal to 0.
Yeah, y by itself is equal to 0. Okay. So those are the conditions. Also, what this is called is a double root. So in fact, if y was actually a polynomial of t and you factored it, it would have the factor y minus t star squared. That's why we call it double root. And if you were to differentiate that, you'd see, oh yeah, the function's 0 at that point and the derivative is 0. So that's what produces this behavior. Whereas here we have y of t star is still 0, but y prime is not. All right. Now, okay. At this point is where I should stop, except for one thing, because so what you could do is because by the time you get to this point, you've solved this. You have some formula for y t that involves y naught, and what you could do is plug in, you can require, you can set your solution that you have equal to 0 at this unknown point t star, and then you can take its derivative with respect to t, and also set that equal to 0 at t star, and you can try solving for your value of y naught from those two equations. That's the most straightforward way to do this problem. So I'm going to give you one more hint. There is an easier way to get the information you need, like y naught and also the value of t star that makes this happen. There is an easier way than that if you take advantage of all the information that's given in the problem. So I'm going to leave it at that and see which among you finds it. So you have a way to get the right answer, but we find an easier way. So any questions about that one? Or any other one from homework?
It needs some clarification on the numbers sort of reading.
From reading questions?
Yes.
Okay. Yeah, actually I figured if there was a reading question someone asked about, it would be that one.
Plus.
Okay. All right. So that's you find two types of two examples of ODEs. One is linear but not separable, and then separable not linear. So as far as which one is like the affirmative, you want to find an equation that is linear, and later you want to find an equation that is separable. You want to fall back on your forms that if it's to be a linear equation, it must be possible to write it in this form, that y prime plus p of ty is equal to q of t, and then separable is y prime is equal to function of t times function of y. And you go back through various examples that we've seen to find equations that are linear or are separable, but to steer clear of a minefield, I want to recall something I discussed before. There is one kind of equation that is both. That is y prime is equal to some function of t times y. So that's the opposite of what you want, which I'm pointing out to steer you towards something that you do want. And actually, this is also worth bringing up because I mentioned the importance of this equation and how it's when it comes up often enough. What is the solution to that? By the way, if you think there's a possibility of having a right answer, go ahead and try. It's better to put yourself out there and be wrong than to possibly be right and say nothing.
One?
What?
One?
No.
What are you asking
What is the solution?
for the linear answer rule?
This one, yeah.
Is that an A?
Yes, it's the a of t. So it's some function of t. And we talked about this sometime last week. Look for your notes if you want.
E to the interval of a t.
Yes, e to the integral of a of t times whatever times some constant, which often will be like initial value. Okay, so even though we're moving past this particular type of equation, moving on to more complicated ones, this one comes up often enough. For example, integrating factors is necessary for that. And then other types of higher equations later on. It's something that just keeps coming up. And to specialize a little bit, y prime is equal to some constant k times y. Y of t would be, so the integral of k, that might be t, the integral of k would just be kt. So you just have e to the kt times the constant. Okay. Alright, they're that important, especially on a test, because you only have 50 minutes, and one brain freeze can really do a lot of damage. Now, I don't put some huge number of problems on my test, but it's enough that it needs to be on top of things, and keep in mind the tips, shortcuts that I give, because and will just help you work more efficiently even outside of the test. Like the shortcut I gave earlier about the power rule, which I'm guessing that your calc instructor had not shown you. You might expect, you can just do the substitution. Yes, you can. There's so many ways to work these problems, but the larger your bag of tricks, the more efficient you'll be. Doesn't really matter whether it's for a test or not.
Is that top C supposed to be multiplied or added?
That is multiplying. So let's put parentheses around this. Okay. Okay. Yeah, I probably should have written C on the left side, so it'll be a little clearer. But, okay. In fact, I'm going to rewrite this in a way that there. So you see the connection between the solution and whatever initial value you might have. All right, we still have time. Are there any other homework questions or reading questions?
On number 21, I was just a little confused as to actually what they wanted aside from the working it out as far as
21.
wages.
Ah, okay.
Oh, the way
Right. Yeah. Part C.
I think it's fancy, but just a little.
Okay. Yeah. Okay. So what can happen in these kinds of problems? There's different types of behavior that you can have. And it's not meant to be exhaustive, but these ones that come up a lot. If you have you can have exponential growth. So it's like a term of a formula like e to the kt, where k is strictly positive. You can also have exponential decay. So same thing, except the constant k is negative. If you end up you have stationary behavior, where y turned out to be equal to a constant. So if there are certain circumstances under which your differential equation reduces to y prime is simply 0, that's called an equilibrium solution. So your solution is constant for all time. It's just equal to the initial value. Now that is something that cannot come up in this particular problem, but it's still something of importance. So, okay. Now, I should mention, I wrote earlier, y prime is equal to ky. In problem 21, you have k is equal to 1/2. But there is this additional term on the right side. So the solution that's written on the other side of the board, that is not your solution, but it is part of a solution. So this is something to keep in mind, that the type of you have these different types of terms that call certain behaviors, but all of these terms, like the e to the kt or whatever, they're multiplied by coefficients. One of those coefficients are 0, then the term disappears, and you don't get the behavior. So that's what's being looked at in this kind of problem, is your solutions are going to be combinations of certain kinds of functions that behave in very different ways. What the particular combination is depends on the initial value. And we'll be looking into this more later in this chapter, that how you can get very different behavior depending on the choice of initial value. You could have exponential growth for one value of a naught in this case, or decay for another. It just depends. So this is about, when you get solution, understanding the behavior. And I'll admit that part A, if not using software of any kind, might be a bit tedious. I would not fault you for going ahead and solving the equation first, because you most likely find that the most straightforward thing, and get an idea there as to how it's supposed to behave. But but it's if you just go ahead and pick different values of t and y and see what y prime is. That you can start with t and y both close to the origin, and start like t and y equal to like 1, 2, etc. Or in this case, you have cosine t. So if you want to set t equal to nice angles like pi over 2, pi, etc., that'd be fine too. To get an idea as to the behavior. Because the direction field, you pick a point ty, and then you plug those into the equation and figure out y prime, and you draw an arrow with slope y prime. Okay. Right. Just about out of time. But so if you continue to have trouble, we have until Wednesday. So just